Hey there, everyone. In today's teaching lesson, I'm going to do something a little bit different. We're going to look at an optimization problem, and this is basically going to optimize how a person or a few people or a group of friends can travel to all 472 subway stations in the New York City subway system in the minimal amount of time and, of course, minimal distance too. Okay, so this optimization stuff is really cool. I've got a couple of videos about optimization. This is considered a traveling salesperson, abbreviated TSP problem. And it's kind of cool because you find out the minimum route or the minimum time taken and the minimum distance traveled for a route to get to all the destinations that you need to go to. So this is a little bit fun. It's kind of practical. I don't know how many people actually do this, although I have heard of people actually going to all 472 subway stations. They try to do it in less than 24 hours. I don't know if they're optimizing the path to go to all 472, but if they did, they could come up with the minimum time and the minimum distance traveled. So let's take a look here and see how this plays out. So first of all, you would need a Google Maps API key. So you can go onto Google Cloud Platform and go ahead and apply for an API key. It's pretty quick. It takes about 30 seconds. You can get an API key. It's totally free. And they give you lots of API calls. I don't know what the limit is. I don't even know. I'm not even going to say. It's quite generous. They give you a bunch of calls. It's not like a couple dozen. I think it's several thousand, maybe thousands and thousands. But if you're going to do this on a grand scale, then they make you pay for it. But in this example, it was totally free for me to get the API key and to do hundreds of calls or even thousands. I think it's totally free. So go ahead and sign up for that. I am not going to run this code. Most of these I refresh the cell so you can see everything that's happening in real time. I'm not going to do that because my API key is confidential, right? I can't share that with anyone here. But you can apply for your own and run this. Just pop it into this thing right here, copy paste it, and everything will run. That's the only change you have to make. I tried to make this example very generic, very dynamic, so it's going to consider all kinds of scenarios. And in full disclosure here, okay, I'm going to be completely transparent. I don't actually go to 472 stations because I couldn't find the data. So I looked around online and spent a little bit of time looking. I didn't spend days and days, but I don't have days and days to spend this. I found right down here, a way to get about 60 stations. So if you can somehow get all 472, you can just copy and paste it into here and you'll have everything that you need. All you need is the station name, the latitude and longitude coordinates. That's it. So as long as you get that, you can optimize the travel time and the distance traveled between all the stations. I'm doing about 60. It will illustrate the point perfectly fine. It's less than 472 just because I couldn't find the data. If you can find the data, God bless you. You're more diligent than I am. I couldn't find it, so I'm settling for 60, but the concept is exactly the same, right? Whether you go to 60 or 472, the code's the same, the concept's the same. It's going to take a little longer if you go to every single one, right? I'm only doing 60, but I think you're going to understand the concept here pretty well. So we have the detailed name of the station. We have the lat long coordinate. That is essential to doing this optimization routine, right? And the address and the place ID, that's pretty helpful too. I don't think we really need that. I think as long as you have the name or the address or the place ID, but you definitely need the lat long coordinate. Okay, that's how this thing is going to run. And these always run the same, right? Latitude, longitude, coordinate. I have several optimization TSP problems that I'm going to make videos for and solve. These are more fun than anything else. I don't think it's super practical for somebody to go to all 472 subway stations. But if you want to do that, that's great. More power to you. You can do that using this program and minimize the time that it takes to do that. So let's go down, look at the station name. I live in New York City, so I understand all these things here. West 4th Street, Washington Square. This is NYU. This is Christopher Street and Greenwich Village, Court Street and Borough Hall. That's in Brooklyn. Okay, so we have the latitude, longitude coordinates. We have the addresses and then the place IDs. That all comes from this right here, the script. When you copy paste this, run it with your own Google Maps API key, you're going to get the same exact results. And I will share this code with you. Right? You don't have to write this down or memorize anything. I'm going to save the file as an HTML file and then upload this when I upload the video so you can access all this stuff and run it on your own Jupyter Notebook environment. Okay, so let's go down and start to optimize the problem. We just imported the data. All we did was import the data for 60 stations. Okay, you always see the row, comma, column over here. This is the standard notation, 60 stations, 5 columns. The columns are name, lat long, address, and place ID, right? So pretty straightforward. So we are going to calculate the haversine distance. This is a standard way to find the distances between latitude and longitude coordinates on a spherical object like the Earth, right? So haversine is a perfect way to look at lat 1, long 1, lat 2, long 2. So this is a source and a destination, latitude, longitude coordinates, and find the distance between them based on sines, arctangents, and some other, what is it called? Trigonometrics, right? I took trig many years ago. Probably forgot some of the finer nuances of this material, but yeah, this is how you do it with the sines, the cosines, arctangents, and so on and so forth. So again, I'll share this code with you, copy paste it, run it on your system, and it'll work perfectly fine. So we get the distances between all the stations, right? That's what this is for. When we when we scroll down here, we'll return the graph data between all these subway stations. So this is called a matrix map, where you're calculating the distances between all the subway stations. So once we have this, we can see what the shortest distance is, and then transverse that distance to optimize the path, right? To minimize the time taken and minimize the distance traveled between all these subway stations. So you need this matrix of all the stations to be able to understand which ones are the closest, which ones are the furthest ones away. But then as you step through all the cells on the matrix here that we've just calculated, you'll see what the closest stations are. You go to those first, and then the next closest become relatively closer as you travel, and then the next ones become relatively closer, and so on and so forth, right? So let's go down a little bit more and look at more of the details. So we are calculating the optimized route and the distance in terms of miles and minutes, right? So these are going to be highly correlated. The more the miles, the more the minutes taken, and vice versa. And it's all based on the longitude coordinates, right? So we have the from station right here, and then the to, and then again the from latitude, longitude, and then the to, so the source, destination, and then haversine, fortunately, is going to go ahead and give us the distance and then the travel time based on the distance, right? So pretty cool how all this stuff works out. It's not super complicated. It's a little bit involved, right? You have to get engaged here to really understand what's going on. But again, just copy paste this, run this on your system, and you're going to learn a ton. I guarantee it. And everything's going to work out just like you see it here. So optimize distance with routes and times taken. We'll start from York Street to Borough Hall. That's 0.5 miles, 0.56, 1.69 minutes. Borough Hall to Court Street, okay, 0.6 miles, so that one's pretty close, 0.17 minutes. Court Street to 36th Street, so these are all in Brooklyn, right? 2.8 miles, so that one's a little bit further, and of course more distance. The further you travel, the longer it takes. 36th Street to Hamilton Parkway, Hamilton Parkway to Atlantic Avenue, Barclays Center, so all in Brooklyn, right? I recognize all these stops. That's down the street from me, and then we get down here towards the end. Grand Central, we go Penn Station to Grand Central, okay, 0.84 miles, 2.5 minutes, no, 2.5 minutes. Times Square to 5th Street, 5th to 59th, Lexington to 63rd, and that's it. Okay, so we did not travel 472. I apologize, I couldn't find the data. If you can find it, that's fantastic. You can run it exactly the same. All you need is the address, the lat long coordinates, and you're good to go. Total distance traveled in this case was 34.13 miles, and total time taken 102 minutes, just over 100 minutes there. So pretty cool stuff, right? So haversine does the whole lift for us, and then Google Maps, right, with the longitude, latitude coordinates. This stuff that seems pretty complicated actually becomes pretty simplified, right, when we engage these tools right here. So again, we're looking at distance traveled, total time taken, travel time in minutes, and then to get the hours, we multiply by 60, right? So that should make sense. Again, we're calculating a distance matrix. So we can find all the distances of all the stations simultaneously, or whatever, I mean, like in sequence. And we can look at this simultaneously and then be able to solve the problem of how to get from one point to the next in the minimum time and the minimum distance, right? So we need this distance matrix. We need the Haversine distance calculation. We need the lat-long coordinates. When we have these key elements here, this becomes a somewhat of a trivial problem to solve. So we're going to go ahead and go down here and solve this using a slightly different methodology. So the first one, let me go back, because the results are going to be slightly different. I did this a couple different ways just to see how similar or how different this was. Okay, so this actually uses scipy.optimize to optimize the problem, right? We are minimizing this problem. This is kind of an interesting library. You can only minimize the problem, right? So you're minimizing the time and the travel distance. You can't maximize anything. But if you wanted to maximize, you wouldn't maximize the time, but if you wanted to maximize something like profit, you would take the inverse of the minimization problem. So you'd make the problem negative, which sounds a little bit weird, but if you look at the documentation and think about it, it kind of makes sense. You can only minimize the problem. You would minimize your risk if you're in a business operations, minimize the time to travel to somewhere, like in this example, or minimize supply chain management, minimize the distance to transport your raw materials or your retail products for supply chain, right? If you're trying to maximize profit, it's the inverse of this problem. You would just put a negative sign in front of the calculation you're trying to minimize, and it would maximize it. So there's something to chew on. You can take that and Google it and find out how that works. So that's scipy.optimize. Let me go back and just look at this problem. This is actually, we are looking at solver. Okay, so this is just OR tools. It's another solving tool. The scipy.optimize is a solving tool. This is another type of solving tool. So this solver told me it is going to take that distance in a time. What did we see? 1 hour? No, sorry, 102 minutes and 34 miles. Right now we're using scipy.optimize. We're going to use a different methodology, but almost everything else stays the same. So let's look at these numbers: 34 miles and 102 minutes. Now let's look at scipy.optimize. Okay, screen blanked out there for a second. Let me go back. 34 and 102. 34 miles, 102 minutes. Everything stays pretty much the same, just a different solving methodology. Okay, and let's see what the outcome is. 34, 102. Let me go down. And now we have, okay, this is horrible, 80 miles. So it did not pick the optimal route by any means. Now we have 80 miles instead of 34 and 242 minutes. So it took almost 3 times the distance, close to 3 times the distance, and close to 3 times the time too. So this is a horrible solution. In this case, it did solve the problem, but it didn't optimize the problem, right? So it tried to, but the first solution was just a much better solution, right? So we have 80 and 242. Now we're going to try one different methodology. This is k nearest neighbor. So we're looking at the nearest neighbor of the matrix, matrix distance or distance matrix, right? The distance matrix calculations. So this is a different way to solve the problem. Instead of using the first solver or the second solver, using k nearest neighbors instead of 34 and 102. I remember that we had 80 and 242. Let's say what k and n does for us. Again, very similar setup, execution, all the same, just different algorithm here. Okay, now let's go down. We saw 34 or 102. That was the best case. Beat the 80 and the 240 or 250, whatever that thing was. Now we have 31 and 90. So look at that, even a better solution, 31 miles and 90 minutes. So before us we saw, I think, 34 and 102. Now we have 31 and 90. So actually the k and n in this case performed the best, right? So this is a good example of using different algorithms to solve the problem. Because if we just stopped at scipy.optimize, we could think, okay, 80 and 100 and, what was that, 240 minutes or something? That's the best way. This is actually the best way, 31 miles and 94 minutes to go to 60 subway stations. Again, coming up short for the 472. I don't have the data. If you find it, great. You can run it. Everything should stay the same. You can copy paste and run it on your 472 stations. I did not have that, so I couldn't do it. Okay, so let us do one more thing. We're going to create a plot now of the distance traveled. and go down a little bit more. Oh, I'm sorry. Yes. So first of all, we look at the optimized route. Okay. And again, this is requiring the Google Maps API key. I can't share that, so I can't refresh this code, but you go ahead and apply for your own. I just copied this and just pasted that in there. Okay. That was all the longitude, latitude coordinates that the code produced for me, traveling to all those stations. And go down a little bit more, and we can plot this on a map so we can see what this looks like visually. I always say a picture's worth 1,000 words. It's totally true. If you just describe what we're doing here, it's going to take 1,000 words. If you show somebody a picture, I think quickly and easily they're going to say, oh, yes, I understand what this is. Somebody's traveling to 60 subway stations, and it's going to take 90 minutes to do that. So we click on this Folium map. I have a lot of videos about Folium maps. You can check out the other videos. Click on this. It shows you the tooltip pop-up here when you click on these little markers, and you can see what the stations are. And this is all in Manhattan. This is downtown, like basically, what is this, Greenwich Village? Not Tribeca, Soho. I'll call that Soho. And then you can see the stations. When I zoom out, you can see it's Lower Manhattan, right? And this lucky person has gone to 60 subway stations, starting in Brooklyn. Let me zoom out a little bit more and going into Manhattan. And everything is plotted out there visually and laid out pretty nice. So that's pretty much it, guys. Optimization, going through 60 subway stations and a minimal amount of time. The KNN algorithm performed the best for us. It outperformed the first two solvers that we saw. And that's it. I'm going to save this file and share all the source code with you so you can copy and save it and run this for yourself, see how it works. It's a great example. Are people doing this all day, every day? No, I think this is kind of a unique example, but it's pretty cool how you can optimize something like this. I have a couple more videos coming out optimizing other types of tasks or other challenges. You can optimize so many different things. So I'm going to describe several of my findings in the next videos I'm going to produce. So that's pretty much it. Hopefully you learned something new today. Thanks for your time, and have a wonderful day, everybody. Goodbye.